Okay, welcome everyone. Thank you for joining. Okay, so we can start. I tried to create the YouTube link for the next hour, but I had some issues and I can't somehow generate it, so I'll have to generate it again on the break. Sorry. So if there's any questions, please. I believe you can all unmute yourselves. So if there's any questions, just unmute yourself and ask. And if you prefer to ask it through chat, please go ahead. And today, Midori Pitini is helping me. So if you'd like to ask a question in a more private way, just send a private message to her. Okay? Don't do it to me because it's hard for me to keep an eye on the chat. So chances are that I won't be able to see it until the break. Okay, if anything is not working, please, let me know so I can fix it. All seems to be fine from my end. Okay, so after a lot of build-up, we're finally going to start talking about complex integration. Okay, this has been like 15 lectures in the making. Right, so today we're going to start with complex integration. Okay, and the sort of amazing thing is that a lot of the things we're going to prove about complex analytic functions or differentiable functions over the complex plane, seems to have nothing to do with integration. However, it will turn out that integration will be sort of the right way to prove all those a lot of those properties, in the sense that there are many properties for which proofs not in trying to sort of avoid complex integration, they become a lot more complicated, a lot more unnatural. Right, so as we develop complex integration, we'll actually be able to from sort of the ideas here and some of the key theorems here, get a lot of the properties of complex analysis that I would like to get, including things like, like every complex polynomial has a zero, or every polynomial of the complex numbers has a zero. Things like this will actually come out of properties of complex integrals, and sort of, after a bit of build-up, of course, but this is sort of a key part of complex analysis, and is a lot of where I would say the more surprising or magical properties of complex functions will arise. Okay, so today we're still going to do most of definitions, because we have to introduce the objects. We have to define what we mean by integrating a function over the complex numbers and all this. So there's still going to be quite a bit of setup, but I think I'll already show you a few maybe surprising things towards the end. Okay, so let's say we have. Right, let's first talk about just integrating functions over the reals, right? Because this is something you learned already in analysis. So let's say we have just a function ft, right, which is equal to, right? So it's a complex number, a complex function, but receiving only real numbers, right? Usually when I write t, I mean t as a real, right? So it's a function defined in some interval, say, right? So let's say that t is smaller or equal, use the same notation, b, and bigger or equal than a. Right, and of course, defining this integral is now quite simple, right? If I want to define the integral from a to b of ft dt, right, this is a little different from the things you've seen before, because these are complex numbers inside the integral, right? But of course, the integral should be additive inside, so it's clear that the natural way to define this is just to define the integral, right, of the real part plus I, the integral of the imaginary part. Okay, so we've already started defining integrals of complex functions, right? They're not yet very interesting because they're still, right, a function receiving a real number, right? So we're only integrating where the variables are real. So we're not quite there yet, but at least now we can make sense of an integral whose values in the integrand are complex. And of course, sort of homework, you just expand everything and you see that for any complex number, we have that the integral, right, and any function, of course, the integral of a constant times a function inside, right, is the same thing as taking the constant and multiplying it outside. Okay. Right, this is clearly true over the reals, right? You probably remember this. Right, over the complex numbers, I mean, it's kind of obvious too that it's true, but you have to work it out, right? So C will be some alpha plus I beta, right? And then inside the alpha and the beta will get something like alpha U minus, right, beta V plus I something, and you just have to make sure that the two things are the same. Okay, I won't do the calculations. This is sort of trivial, but this is true. Maybe I'll take this so that you don't think it's a V. Okay. Okay, we also have, let's look at more interesting properties of it. In particular, there is a triangle inequality, right? So when I write this, I mean a triangle inequality. Right, and this triangle inequality is that if A is smaller than B, then let me maybe just to, I don't, for now at least, I'm not so worried about exactly what amount of regularity I need out of my functions, right? In the sense that it's not necessarily my interest to go to requiring as little regularity as possible. Let's just say here that f is continuous, like throughout, just so that I don't have to worry about defining the integrals and all this. Okay. Okay, so then what can we say? If a is smaller than b, then the integral of ab, the absolute value outside the integral, gives you a number that's smaller or equal than if I take the absolute value inside the integral. Okay, right? This is the famous triangle inequality, right? Taking the absolute value outside of the sum gives always something smaller than taking the absolute value in each one of the terms of the sum, right? And the integral in the end is just a sum, right? So how do we prove something like this? Okay. So first, if this integral is 0, ab f of t dt is 0, then it's done, right? Then, right, there is nothing to prove. Then we are done, right? Because this is 0, and this is the integral of a real function who's always bigger or equal than 0. So for sure this is bigger than 0, then we are done. Okay, so let's go to the more interesting case in which integral ab ft dt is not 0. Okay, if it's not 0, it has an argument, right? So let's say that theta is equal to its argument, right? The angle in the complex, right? If I think of it in the complex plane, this is a number, so I can take its argument, right? A, B, ft, dt. Okay. Okay, let's say this, then let's define this way. Okay, so now I want to, right now I can write this absolute value. Right? If I grab this number and I sort of rotate it by minus the argument, it becomes a positive real. And if it's a positive real, it's equal to its absolute value. Right? So this is the same as doing the real part of, right, exponential of minus I theta, the integral right? Because this was the argument of this, right? This is just a number. This thing in orange is just a number, right? It's an integral, but it's a number. It doesn't depend on anything. This is its argument, right? Theta is his argument. So if I multiply by exponential of minus I theta, the argument of this is 0. This is a positive real. And so its real part, because it's a positive real, is the same thing as the absolute value. Okay, now I move, the real part and exponential inside the integral. Right, so I get a b. Let me see if I can make sure that there's a separation here. Right, a b, real part of, right, exponential okay, but now, right, now this is an integral over the reals, right? So if I take an integral of something that's real, because this is a real part, this is for sure smaller or equal than the integral of the absolute value of what's here, right? Because this is always smaller or equal than its absolute value, right, of the same thing, right? But the absolute value of this has absolute value 1, right? The absolute value, maybe. Okay, so I have the real part of something, right, is always smaller or equal than the absolute value of the real part of something, but in particular also the absolute value of simply what's inside the real part, right? Because the real part is always smaller or equal than the absolute value of the number. Okay. But now we know that the absolute value of the product is the product of the absolute values. An absolute value of an exponential of a purely imaginary number is 1. So this is smaller or equal than just the absolute value of f of t, right? What's inside the integrand. And because these are all reals, the integral also needs to satisfy this. Okay, this is a very simple inequality, but right, it's nice that you can, sort of prove your result by just saying that, right, the neat trick here is that the absolute value is just you grab your number and you rotate it back by whatever was the argument, right? Okay, so we have triangular inequality, so that's good. Okay, so let's keep going through more and more properties. Okay, so for now, we were just integrating. So I just noticed someone asked, why can we take the real part inside the integral? Okay, so this is a good thing for you to check too, right? By looking at, from this, right, from what we wrote, that if I have, right, that if ft is equal to ut plus ivt, right, that this integral would be the integral of ut plus I, right, vt. Oh, I should put dt's everywhere. Right? What is the integral? What is the real part of this integral? Right? The real part of this integral, well, remember, these ones, right, ut and vt are all real. Right? And so this means, in particular, this is the integral of something real is also real, right? This is the integral that we know and love from real analysis, right? This is also real. In particular, this means that the real part of this, right, is equal, right? There's something that's real plus I something that's real, so the real part of that is exactly this, right? Which is exactly the integral of the real part. Okay? And basically, when you try to show that you can multiply by a constant, I mean, you'll have similar types of arguments. Okay. All right, thanks for the question. Okay. Okay, so now we will right, so now we don't actually just want to integrate functions that go from an interval, right? F, in a way, goes from some interval, say, AB, to the complex plane, right? So we're still doing very much real analysis type integral, right? Because, sure, it takes values in the complex plane, but, you know, it's still receiving real numbers. So we really want to now integrate over paths or arcs. Right? We now really want to integrate over, say, paths or arcs, right, in the complex plane, right? And that's why we sort of try to develop a bit of the math around arcs in the complex plane and so on. So let's say that I have some arc gamma, right? Let's represent this arc, right, parameterized by zt, where z is, try to use the same notation as much as possible. Okay, so let's say I have arc zt that's parameterized by t from a to b, right? So maybe picture always helps, right? I have some arc. Oh, this is yeah, sorry, yeah, not the very most clever choice of arc because it looks just like an integral sign. Okay, so, right, this could be an arc. This could be the arc gamma. And this could be, say, right, z of a, right? This maybe would be z of something else, some other t, right? And z of b is the end of the arc, right? And this arc is being taken this way. Okay, right, so something like this. Okay, let's say that f is continuous. Okay, let's say that f is continuous on z, on the arc. Okay, then we define, right? We sort of define the integral over the arc in exactly the natural way, right? So we define the integral. Let's say, okay. So we define the integral over the arc of f z dz, right? Exactly as we use the definition that we had from the integrals over the reals, right? So this will be the integral from, right, on the parameterization from a to b.
Sorry?
Yes?
Sorry, someone asked, did we define that arcs can self-intersect, and would it be ever problematic?
So for now, good question. It would not be problematic, at least for some things. It would, yeah, the short answer is it wouldn't be problematic, at least for a lot of the things we're going to do now. However, I sort of been drawing all of them not intersecting because it's easier. There are some things that get a bit trickier if they intersect, right? Because then a point might get, might have two values of the parameterization in it. But most things are actually don't have an issue. Right? Yeah, so what a bigger issue is when you have that, right? A bigger issue is when the parameterization sort of, right? You could imagine the parameterization going and parameterizing and then deciding to go back and then back up, right? As t varies, if you think of the point moving, right, moving up and then deciding to go back and then go up, this would be sort of more problematic than just the curve self-intersecting. But most things you can do without the curve self-intersecting, and most of the times that's what we mean, but there's actually no problem if they intersect, at least for now. Okay, we defined at some point the name for a curve that doesn't self-intersect, but now I don't remember the name. Okay, but it will come back to me. All right, okay, but it's not really a problem at this point, no. Okay, but yeah, it's a good question. Okay, so how do we define this? We take it over the integral from a and b, right? F of zt, right? And now we need to take, right? We want to make this integral dt. It's like doing a change of variables. We need the derivative of z with respect to t, right? The derivative of the parameterization. And that's why we often need that our paths are differentiable, right? We need these paths to be differentiable, the parameterization. Okay. So now what should be sort of the question screaming at us, right? So, okay, so we've just defined the complex integration, basically, right? This is complex integration. Okay, so we've essentially, it's defined. We define complex integration, integrating a complex in continuous function over the complex numbers over an arc, given its parameterization, is given by this integral. This is an integral that, it's an integral defined over an interval of the reals, right? This, of course, is a complex number, a complex function depending on t, the derivative. This is also a complex function, but goes back exactly to this definition, right? So this appears at least well-defined. Right. So now, what's sort of the screaming question? So while you think about the screaming question, maybe it's worth saying that if gamma is only pointwise, so it's only pointwise differentiable, right? It's a good observation to make. If gamma is pointwise differentiable, then we can define the integral pointwise, right? That's no problem. Not pointwise, sorry, piecewise. Right, so if it's piecewise differentiable, think, right, some like it's differentiable, and then it has a kink, and then it's, right, something like this. Right, and so we might have kinks here, here, and here. Right, so if it's piecewise differentiable, then we can define the integral piecewise. Right, the integral over the curve, we can just define it as we take the integral here, plus the integral there, plus the integral there, or something like this. Okay, we'll see this a bit better in a second. Okay, so any suggestions for what's sort of the screaming question at the moment? Right, that we really ought to address? Exactly, right? So someone suggested reparameterization, right? It better be that, we started talking about arcs and we sort of draw the arc, but not always write its parameterization. So it better be that it's invariant with respect to reparameterization, right? So sort of the screaming question is it invariant with respect to reparameterization? Okay, because if it's not, then it's not a very good definition, right? If the integral is valued differently, depending how I decide to parameterize my curve, then it's really hard to talk about values of integrals of curves, right? Because then they come with the parameterization, all sorts of issues arise. Okay, so let's just work it out, right? Let's write a reparameterization. So let's say that I have zt. Okay, let's say I have a reparameterization. Okay, so I'm going to define t of tau. Tau is going to be my new variable. Tau is going to be between alpha and beta, right? And the idea that, this reparameterizes that interval, right? So t of tau, right, goes basically, think of it as a function that goes from the interval alpha beta to the interval ab, right? With t of alpha being a and t of beta being b. Okay, and everything differentiable. Okay, so let's try to work out these integrals now. Okay, so let me see if I have enough space. Maybe I'll erase over there to not to cram what I'm writing. Right, so let's say that I'm writing the integral now on that new, right, on this new representation. So I'm going to write the integral on this new representation. I'm going to write it here, and then we'll work it out over there. Right, so it's the integral from alpha to beta, right, of f at the point z of t of tau, right? Because now the new curve, right, the new curve is z of t of tau, right? Right? We can think of this as t, or this as sort of being the new curve, right? It's now a curve of tau. Okay, did I miss? I think I forgot. I think I have one parenthesis too few. Okay, and now I need the derivative, right, with respect to tau of this new parameterization, right, of z of t of tau, right? Because this is my new curve, right? We use the same colors, right? And then d tau, right? In our definition of complex integral, this would be the integral of f around the curve in this new parameterization. Okay, right? Right? This would be the integral f z dz given in this parameterization. Okay, so now we'd like to show that the integral didn't change, right? That it's still the same one as the one in right, as the one of in the original parameterization. Okay, so let's do that. Okay, so let me write everything again so that everything is here. Z of t tau. Okay, derivative with respect to tau of z of t of tau. Okay, dt. Okay, now, okay, let's do one thing at a time. Chain rule first. Take away this derivative. It's the kind of thing that's easier, I think, maybe for you to do it than watch someone else do it, but let's do one at least. Okay, right, so if I take the derivative, this is z prime at the point t tau times t prime at the point tau, right, by chain rule, dt. Okay, but now I can do the change of variables, t to tau, right? Right, let's do change of variables. Right, as we learned in real integrals, right? And if we do change of variables, then we want to write this now as an integral over t, right? So now this is, it's alpha and beta, sorry. because this is the integral in tau, alpha beta. Okay, so now we're going to do it, the change of variables to use, oh, so many typos, sorry. Okay, this is that. Okay, so this is tau. This is also tau. Okay, let's look at it. Let me look at it from a distance, make sure everything is right. Okay, this is just the integral defined on the parameterization tau, right as here. All I did here was I expanded in using change rule. Right. And now I'm going to do my change of variables, right? It's going to be an integral now on the variable t. So it's an integral that goes from a to b, right? F of z of t, right? Z prime of t, right? And now we have exactly t, the derivative of t, so right, dt d tau times d tau, right? And so this is exactly dt. Right, so basically the way we define the integral over the curves, because it has that derivative there for the path, it makes it invariant with respect to reparameterization. Right, this is exactly the integral over the arc of fz dz. Okay, so we proved that complex integration over the arc is invariant with respect to reparameterization. Right, this is crucial because now we can talk about integrals of an arc, right? Then rather than integrals of a parameterization of an arc. Okay. Okay, so maybe before I talk about another property, let me just say a word about the question I was asked a few minutes ago about whether, right, whether you can consider arcs that intersect themselves, right? So definitely you can, but I would even take this question a step further and say, are we going to be in a position where we should be considering such arcs? Right, because maybe we can just make the arc avoid itself most of the times. But let's say that you have a point, right, and somehow you want to loop around the point twice. Right, I want to say a closed arc, an arc that starts and ends in the same place and loops around that point twice. Right, if you think about it, you won't have a chance, right? You're going to have to start thinking about arcs that intersect each other. Right, and it's going to be important to look at curves that sort of loop around points more than once, and so on. And so these kinds of self-intersections of this type are going to happen quite often, actually. Okay. Okay. So more properties of properties of the integral. I think now is okay. Oh yeah, someone spotted the typo of d tau, but sorry I didn't see it in time. But yeah, too many letters in this integral not to get at least one wrong. Okay. Okay, so let's see what happens in the so-called opposite arc. Right, so we define given an arc, right? Let's say the player in this game, right? So this is some arc. I'm going to try and use this notation as much as possible, right? Some parameterization from A and B. Let's take the arc. Let's take the opposite arc, right? So just the arc that does gamma, but parameterizing it exactly the opposite way, right? minus gamma, right? And so we can just take the arc z, right? So the right way to parameterize this is z of minus t with right, with t between minus b and minus a. Okay, so as when t is minus b, it starts, right? So if I have some arc, let me use another color. Right, if I have some arc like this, the opposite arc is just the one pointing the other direction. Let's see if I... Okay, so let's see what the integral of the opposite arc is. Okay, so let's take integral of the, okay, of fz dz, right? So what is this? This is the integral from minus b to minus a, right, of f of z of minus t. Now the derivative z of minus t, right? The derivative of, right? So there's a the minus here from the derivative of the minus z. Okay, but let's say that now I do the change of variables to go from t to minus t. Right, so what is this equal to? Right, then I have the integral from, right, b to a. Right, this minus is from the d minus t, right? So fz of t. Okay. Now, right, I'm swapping t by minus t, so I have to multiply by minus 1. So this takes me that minus over there. Maybe I should have used u equal to minus t, okay, because, okay, here, right, if I had used u equal to minus t, here I would be using u's, here I would be using t's, dt. Right, but now this is the integral exactly of the curve, but start going from b to a, right? But we know that this is minus the integral pointing in the other direction. Right, this we know from integrals over the real numbers. See. Okay, so this is equal to minus the integral over the normal path, right? Because this is the integral over the original arc. Okay, just like over the reals, integrating with respect, right? Integrating with respect to the opposite path just gives you minus the integral in the original path. So integral over the opposite path of, say, f e dz is just equal to minus the integral gamma of fz dz. Okay, just like over the reals, when we integrate on an interval, or the interval parameterized the other way. Okay, because keep in mind, right, this is not a reparameterization of the arc, right? This is now a different arc, because when we had an arc, we had also its direction. Okay, make sure I don't forget anything. Okay, so another important property, and then I think we'll have to take a break soon, right, is that clearly I can think of paths. Let me draw a few more. Right, I can think of a path. Right, I can think of an arc 1, and then, right, continued by, say, an arc 2, right, as long as the starting point is the same as the end point there, and continued by arc, say, 3. Right, and I can think of this whole thing as some arc, gamma, right? And I can write things like gamma equal gamma 1 plus gamma 2 plus gamma 3, right? If the endpoint if the starting point of gamma 2 is the same as the endpoint of gamma 1, then I can talk about adding arcs in this way. And clearly let me see. I could also talk about it not even without the endpoints, right? But then it's not clear exactly what I mean by that arc. So let's imagine it with the endpoints being the same, right? Then it's clear that I have properties like this, right? If I have integral of, say, alpha, like gamma 1 plus gamma 2, so on, plus some gamma n of system FDZ. Is it okay? Is it working now?
Yeah, now it's working, I guess, for everyone, I hope.
Yeah, let me see if on YouTube is also okay. Yeah, looks okay. Okay, all right, thanks. Yeah, if any of the others can see, please, yeah, let me know here. Okay, and so, right, so if I have an integral over a sum of paths in this way, then this is clearly equal to the sum of the integrals, right? This will be important. Right, so here I stopped writing f of z, but it's of course still f of z. Okay, so in the last 2 minutes, let me just say that if, okay, just another property, right, integrals over closed arcs, over closed curves, don't depend on starting point. Okay, what do I mean by this? Let's say I have an arc that does this and goes back and starts here. Right? In the way that I defined arc, I have to say what is A and B. Right? Let's say that this is the starting point, right? So this would be both A and B, right? This is the start of the arc. Right? And so this gives me some arc, say, right, gamma, but I could instead, right, take this same curve, but instead mark the start point and end point here, right? And just go from here and go around and come this way. All right, and this a priori might not look exactly like the same arc, so it's important to argue that the integral over any of these arcs is exactly the same. Right, so let's call this gamma and this one here that starts here as gamma prime. Okay, so why are they the same? So this is a very easy thing to see, once you see how it's done, right? Take this starting point and that starting point, and let's call this part of the arc gamma 1. Right? It's now an arc that starts in this point and ends in that one. And let's call this part of the arc gamma 2. Okay? The integral over gamma, and I won't write FZ dz, it's clear that it's there. The integral over gamma is what? Is first I integrate, right? First I integrate over gamma 1, and then I integrate over gamma 2. Sorry, this is 2, of course. Right, but because addition is commutative, right? Of course, this is the same as integrating first over gamma 2 and then from over gamma 1. Right, but this is exactly the integral over this arc, right? It was exactly the same arc, but the one where I started and ended in this point. Okay, and so integrals over closed curves don't depend on starting point, right? And we had already seen that we could reparameterize a closed arc in a way that the starting point would change, right? So if we have some kind of closed curve, right, like this, some closed curve arc, we do not actually ever need to specify what's the starting and ending point. Okay, and integrals over closed curves will actually be extremely important, and I'll explain why after the break. Okay, I'll stick around if there's any questions, and yeah, thanks. And I'll send a new link because somehow I had trouble creating it beforehand.